So welcome to the special year seminar on theoretical machine learning at the Institute for Advanced Study. Today, we are delighted to have a scientist as distinguished as Professor Shai Ben-David as our speaker. Shai is a professor at the David Cheriton School of Computer Science at the University of Waterloo and is known for his broad array of fundamental contributions to learning theory, algorithms, and complexity theory, including in the theory of domain adaptation, clustering, learnability of multi-value and real-value functions, change detection, and alternatives to worst-case complexity. Shai has served as the president of the Association for Computational Learning Theory and is also the co-author of the acclaimed textbook, Understanding Machine Learning from Theory to Algorithms. Please welcome Shai Ben-David.
Hi. Okay, so I want to talk today about learning distributions and what can be done and what cannot be done. And it will basically looking at the following problem. So, I mean, what is the basic problem of statistical learning? You have some unknown probability distribution, which could be the environment. And then we see a sample of this distribution, empirical data. And based on this sample from the unknown distribution, we are trying to learn as much as possible about the distribution that generates the sample. So this could be described as the very high-level statement of what is statistical learning about. Unknown environment, you get a sample, you want to learn as much as possible about the environment from the sample. So the first two questions to ask in this setup is, first of all, is what prior knowledge the learner comes with. And the second one is, what is the goal of the learner? What does the learner try to deduce about the distribution? So the most ambitious framework is saying the learner starts with no prior knowledge at all. He makes no assumptions about how the data is generated. And the learner aims to find as much as possible about the distribution. Basically, the learner aims to figure out what the distribution is, to come up with a distribution that is close to the data generating distribution. So that's the most ambitious goal. I mean, we come with no prior knowledge and we're trying to figure out what the distribution is. The problem is that in this is kind of the setup. You have an unknown distribution D, it generates IID samples, and the learner has to come up with some D hat, which should be a close approximation of D. The problem is that in this very ambitious setup, it's provably impossible. And it's very easy to see why we cannot give any guarantees of success based on finite samples. So here is an example of why it is not possible. Consider that you just have a discrete domain set X, and let's denote the size of X by capital N. And now assume that I take a sample which is less than square root of n many sample points. So we know that if the sample is so much smaller than the size of the domain under the uniform distribution, we are likely to see no repetitions. But if we get a sample without repetitions, we cannot distinguish between the case that it was generated by the uniform distribution over X or the case that has been generated by uniform distribution over some subset of X, say of size n over 2. So there are two very different distributions. Both of them are just as likely to have generated the data that we have seen. And notice that the size of the data here is a function grows with the size of the domain. So if we want guarantees bound that are independent of the domain size, sample sizes independent of the domain size cannot distinguish between very different sample generating distributions. So this is just my motivation to saying we cannot start without any prior knowledge and hope to get a good approximation to the data generating distributions. So as a result of this observation, there are two directions to do research along, two questions to ask. So one direction is you will make assumptions about the generating distribution, and then you try to see under those assumptions, what can you learn? So for example, you assume that the data is generated by a mixture of Gaussians, and now you have better control, and maybe you can get guarantees of success. The other direction is say, I will not make any assumptions about how the distribution is generated, but instead of being so ambitious and trying to find what the distribution is, I will only aim to answer certain questions about the distribution. Say I want to predict the likely labels, I want to predict cluster structure, I want to find the means of distribution, and so on. So these are kind of two relaxations of the problem. Either we make prior assumptions, or rather than trying to learn the distribution, we just settle for answering some questions about the distribution. So in this talk, I'm going to give one result on each of those two directions. So in what I'm going to talk about is the first result is learning mixture of Gaussians. So it's a very common data generating model, a mixture of Gaussians. And we are going to have a positive result with Hassan Ashtiani and Nick Harvey and Chris Lowe and Abbas Merhabian and Yaniv Plan, settling the sample complexity of learning mixture of Gaussians in RD. The second part, I will talk about the second situation in which we make no assumptions about the distribution, but we only try to answer certain questions about distribution. And here what we will show is that it is impossible to characterize which questions you can answer and which not. So that will be the second part, and this is work with Pavel Hubs and Shai Moran and Amir Shpika and Amir Yehudayev. So let me start with the first part. So the task is learning density estimations of restricted family of distributions. This is very fundamental and well-studied problems with many applications. And the simplest case here is learning Gaussians. So assume that your data is generated by a Gaussian. You're trying to find the parameter of the Gaussians. It's a Gaussian in RD, so we know that we roughly have these square parameters, and it is well known that by sampling d square over epsilon square IID points from this Gaussian, we can recover the Gaussian up to an L1 distance of epsilon. So the case of one Gaussian is well known. And now the question was, what happens if you try to learn a mixture of k Gaussians? So the conjecture, the natural conjecture is again that it'll be the number of parameters divided by epsilon squared. So epsilon is how close we want to approximate distribution. And kd squared will be now the number of parameters because we have k Gaussians in RD and each of them requires these square parameters to determine the Gaussian. And this is the result that I'm aiming to show. Just note that when people talk about learning a mixture of Gaussians or parameterized distribution, there are two different lines of research. One of them is trying to recover the parameters. The other one is trying to approximate the distribution. So here we're talking about the second one. We're trying to approximate the distribution to come up with some distribution which is close in L1 distance, so total variance to the original one, not to recover the parameters. These are different problems. Okay, so my goal now is to show how we can settle for kd square over epsilon square examples. This is the main contribution of this paper. O of k squared d square over epsilon square suffice to learn mixture of k Gaussians in RD. And we also get a lower bound, which up to logarithmic factors is completely matching. So it resolves the question of the sample complexity of learning mixtures of Gaussians. So the main technical tool that I'm going to use is the same tool that I'm also will use in the second part of the talk. And this is the notion of sample compression schemes. So sample compression schemes can philosophically be thought of as manifestations of Occam's razor. And they were introduced initially by Littlestone and Warmuth in '86 for the case of binary classification prediction. And they showed that if you have sample compression, then you can learn. And then almost 30 years later, Moran and Yehudayev shows that if you can learn, then you always have sample compression. So this was introduced for binary classification. And for binary classification, it solves the problem. You have compression if and only if you have sample compression schemes. So what we are going to do in order to learn distributions is to introduce a sample compression scheme for learning distributions, for the density estimation. So basically, we can think of sample compression as a game between Alice and Bob. So we have a class of distribution. We said that we are in the domain where we make assumption about the class of distributions, say Gaussians or mixture of Gaussians. And one distribution from this class is being picked. And Alice knows the distribution and knows the class. And Bob only knows the family, but he doesn't know which distribution was picked. So he knows it's a mixture of Gaussians, but he doesn't know which one. Now, Alice generates IID samples from this unknown distribution, and the compression scheme is some agreement between them. She will pass to Bob only few of those examples. So they are only allowed to communicate by sending few of the examples that were generated randomly. And the compression scheme is successful if from these few examples, Bob can reconstruct a distribution which is close to the data generating one. So we say that the family F has a compression of size T if Alice can set at most T points, and with high probability, it will allow Bob to approximate the generating distribution for any distribution that comes from this family. So it's a property of the family having a compression scheme. So here is an example. Here is a compression scheme for a single Gaussian in one dimension. So assume that I have data so Bob knows that it's a Gaussian, but he doesn't know which one, and it's over R. So now Alice generates a random sample. And if you generate a large enough random sample, then you can show that with high probability, there will be 2 points such that the average of those 2 points is close to the expectation of this Gaussian, to the mean of the Gaussian. And the difference between these 2 points is a good approximation to the variance of the Gaussian. So Alice can just send 2 points to Bob, and Bob will just take the average and know a good approximation to the mean, and he will take the difference and get a good approximation to the variance. So we show that Gaussians, single Gaussians in R can be compressed to 2 points. Now, how does it relate to learning? So there is a theorem here that says that if a family has a compression of size T, then you can learn the family up to epsilon in number of examples, which is T over epsilon squared. So small compression schemes imply efficient learning of algorithms for distributions. The proof idea is roughly, so I mean, we don't have Alice. Alice knows everything, but we are just Bob. We only know the family. But what we can do is we can simulate Alice. We can consider all possible T tuples. We generate a sample. We consider all possible T tuples. So there's at most M to the T such T tuples. And for each of them, we do the reconstruction. And now we have a finite family of distributions to pick from. And we just serve some part of the training sample to decide which of those candidates is the best approximation. So basically, it's a very simple idea that if you have a sample compression, then you have learnability. Bob can just simulate Alice. Now, the advantage, the big advantage of the sample compression scheme is it is very modular. If I can learn one family, I can learn all kinds of combinations of this family. So here is the first result. Say I want to learn a compression of mixtures. So I have now, I want to compress mixture of Gaussians. So now it's not a single Gaussian, but it's a mixture of k Gaussians. So this mixture generates samples. So Alice will generate the samples. Now Alice will pick 2 points to represent each of those distributions. So we can see that we can compress a mixture of k Gaussians to just size k, order of k times t, if we could compress one distribution to t. So we see here that the notion of compression is very modular. I can go from compressing a family of distributions to compressing k mixtures of this family. So the result is that if I have a compression scheme to f of size t, then I can have a compression scheme of size k, order kt to k mixtures, and therefore I can learn k mixtures in kt over epsilon square, because we said that the sample size for learning is just the compression size over epsilon square. So small compression schemes imply sample efficient algorithms for mixtures. So now we are only missing one component. We know that we can compress to 2 points Gaussians in R. The question, and we know how to combine it to mixtures, but we want to do mixtures not over R, but mixtures over RD. So the question is, how do, yes?
Just a quick question. What about the mixture weights? Here, this reduction assumes equal mixture weights, but what it,
Right, so that's a good question. What about the mixture weights? So that's why the tilde over the O. We can show that with just logarithmic number of bits, you can give good approximation to the weights. So the whole point is that the family of candidates is small. So in order to approximate, so that's a good technical point, but we can put into the compression a small message, as long as this message is logarithmic in the size of the sample. And that will give you approximation of the weights. Okay?
Thanks, yeah.
Okay, so now how do we do it in high dimension? So for every 2 coordinates, we want to learn the 2-dimensional ellipsoid Gaussian with this variance and this mean. So we can see that we generate a sample. We pick 2 points to determine one direction. We pick 2 points to determine the other direction. So we see that we can learn this covariance of two coordinates with just a constant number of sample compression. And therefore, if we want to learn a Gaussian, a single Gaussian in d dimensions, we have d square many covariance coefficients. Each of them requires a constant compression. So now we know that we can compress to order of d square Gaussians in RD. So now we have all the components to get our results. Now,
Shai, I just have a quick question. In the one-dimensional uniform mixture case that you mentioned, are you allowed to color the points when you send it, in the sense of being like, these two correspond to this Gaussian, these two, or do you just, if you just send 6 points, how will the person know which two to add and subtract?
Yeah, so this is very similar to the question that Samori asked, and that's that I allow a side information, as long as the side information is only logarithmic in the sample size, then it wouldn't change the translation from compression to learnability.
Okay, got
so
it.
I allow on top of it side information.
Okay,
and
one
the
more
side
quick
information is still log m, because so it's logarithmic in the size of the sample.
Right. So basically, you're allowed to send colors also and things like that. So
Right. I can allow to send everything, anything. I mean, the small sample plus logarithmic in the sample size bits.
okay. So and just again, a clarification is there any limit to the number of points that Alice is allowed to sample before choosing T of them to send across?
Okay, that's a good question. How many points does she need to sample? And that's another technical point. And we will have it come somehow. You can fold it down into the sample compression, but it's a good point. You cannot do it with too few points.
Right.
But yeah, it's another technical small thing that we have to overcome. It kicks in only from a certain sample size, which is big enough to get with high probability the representative points. Right.
Right. Okay. So but when you say like the family F has a compression of T, if you know T bits suffice for, when you say that there's some underlying implicit thing also where the person needs to sample enough number of points to pick T points from.
Right. So we call it an MT compression.
Oh, I see. Okay.
We have actually a third parameter, which is the number of hint bits so there are 3 parameters. What is the original sample size you have to start with? How many of them Alice is going to send? And what is the length of the string of bits of hints that you have to attach to it?
Okay, great. Thank you.
That's 3 parameters. To make it clear, yeah.
Okay, thank you.
But these are very, very good questions, yes.
So we have
so now with this.
We have another question on the chat.
Yes.
So this is from Shushan Agarwal. Do Alice and Bob also have to agree on scheme beforehand, or is the scheme also encoded in the log number?
No. They have to agree on the scheme beforehand, but the translation from compression to learning is not bothered by this, because what we do is Bob knows the scheme, he just samples points, and now he simulates Alice, and for any T points, he uses the scheme in order to come up with a distribution candidate. So they agree on it, they have to agree on it before, yeah. But it's not limited. It could be any function that goes from small sample sizes to candidate distributions. Okay? So with this simple idea of compression, we got the bound that we were shooting for, that in order to learn a mixture of Gaussians, all we need is the number of parameters, KD squared divided by epsilon squared. And in this paper, we also got a matching lower bound. So it basically completely resolves the question of the sample of complexity of learning mixture of Gaussians.
So Shai, you actually said that there is a difference between this one and estimating the parameters, but all your examples, what you did is estimating the parameters. So I'm not sure what the difference is.
Oh, the difference is that, yeah, it sounds like I got estimation of the parameters, but when the parameters are such that, you know, we know there's indistinguishability of parameters. So we can show that this can be overcome by just the compression will give you say a single Gaussian instead of 2 Gaussians that are mixed together, which are too close to distinguish between them.
Right. So you don't care about the number of Gaussian actually. It can be. This is given.
This is given, yeah.
Yeah, so some sort of hierarchical mixture with the number of Gaussians actually changing with the data is not in this game.
So then you have to do, you know, those tricks of trying different Ks and making sure that you're not overfitting, right?
All right.
Yeah, good point.
But the part of the difference is this result doesn't require some separation.
The result does not require separation. That's the point here, yeah.
Whereas the parameter estimation would.
The parameter estimation would, right.
Thanks.
And yeah. And in some sense, I mean, there could be a good parameter estimation, which is very bad in terms of the L1 distance. If you have 2 Gaussians which are very close, but each of them is very narrow and sharp, then if you miss approximation, if you confuse them, in terms of parameters, it's not much difference. In terms of the L1 distance, it's a lot of difference. So in some sense, it is demanding the learning with L1 distance. Okay, so this kind of summarizes the first part. So we introduced notion of compression framework for density estimation. And as application, we improved the bounds for learning mixture of Gaussians and got a tight analysis of the number of samples needed to learn mixture of Gaussians and the matching lower bound. I think there are two natural questions to ask. First of all, it seems that this technique could also be used to other learning of mixtures of and other distributions, and there is a natural way to extend it. We have not followed it, but I think it's an obvious thing to do. The other big question that is still open is the computational efficiency of those algorithms. Because here, the algorithm just simulates all possible m to the t candidates. And this is not going to be efficient because t depends on the dimension. So it's going to be, so we don't give here an algorithm which is sub-exponential in the dimension. So that's a kind of a orthogonal question. What is the computational complexity, which is still wide open? Okay, so that concludes the first part. So just to remind you, the first part, we made assumptions about how the distributions were generated, and we're trying to learn the distribution. In the second part, we are going to talk about making no assumptions about how the data is generated and asking what kind of information can you extract without making any assumptions. So the question is, what types of information can you learn without assuming any prior knowledge? And the general learning problem is basically was already phrased by Vapnik. You have a collection of real valued functions. You can think of them as queries or random variables over some domain X. And you get an input as a sample, which is IID generated by some unknown probability distribution over X. And you want to estimate those random variables or those queries. So if you want to estimate every single one of them well, this is the uniform convergence problem. And this is a problem that is well understood. We have dimensions like the pseudo dimension, the VC dimension, that tell you when can you do uniform convergence, when can you estimate all of those variables simultaneously. But there is an interesting variant here, which is sometimes we are not really interested in estimating all of the random variables. We just want to find one that has the maximum expectation. So we call it the expectation maximization problem. It's a easier problem. You have a collection of random variables or real valued queries over some domain X. You get a sample, and you want to find which random variable has the highest possible expectation, or approximate the one with the highest possible expectation. So this problem is very, I mean, it can encompass many problems in machine learning. For example, binary classification, you have a collection of models. The random variable is the loss of each of those models. You want to find the model with minimum loss. And it applies to multi-class prediction as well. There's nothing here which is binary. You just have a collection of models. You have a notion of loss. If the loss is expectation over points generated by distribution, you have this problem of you want to find a model that minimizes the loss. Same for k-center clustering problems. So a model is k-centers. For every k-centers, you have the expected loss. Could be k-means or k-median or whatever. And you want to find the k-centers that minimize the loss. So notice that in all of those problems, we have a collection of random variables. We are not interested in estimating all of them. We are just aiming to find one model that close to minimizes or maximizes the expectation under the unknown probability distribution. And there are many other cases that fall under this general framework of expectation maximization problems. So let me talk a little bit about how are we going to address this problem. So the tools that we know from binary classification, we have PAC learnability, we have learnability with empirical risk minimization, just minimize the risk. We have weak learnability, we have uniform convergence, we have compression schemes, we have dimension like the VC dimension. In the case of binary learning, all of those are equivalent. A class is PAC learnable if and only if you can learn it with ERM, if and only if it's weakly learnable, and so on. All of those conditions are equivalent. So in the simple case of binary classification, the fundamental theorem of statistical learning tells you that given a class, all the above are equivalent. They're all equivalent to the finiteness of the VC dimension. And this equivalence even holds quantitatively. We know that the VC dimension can tell us the compression size, can tell us the learning rates, and so on. Now, what happens if we go beyond binary classification? As we saw, the expectation maximization is a much wider family of problems than just binary classification. So it turns out that it breaks down already when you do multiclass. So in a paper in 2010 with Amit Danieli and Sivan Sabato and Shai Schwartz, we showed that in multiclass, you have different ERM algorithms which give you different learning rates. And there could be a class that is learned by one ERM algorithm, but is not learned by other ERM algorithms. So going from two-class problems to multi-class breaks this beautiful equivalence of all the conditions of the fundamental theory of statistical machine learning. It applies to binary classification. It breaks down in the more general case. So now, here is another example where it breaks down, a very simple example. So now look at the following task. You have a collection of subsets of some unknown domain set X. And the expectation maximization problem is you want to find one subset whose probability weight is close to the maximum weight in the family. So you have a family of subsets. These are your queries. You want to ask which of them is most likely to be hit by the probability distribution based on a finite sample. So I'm looking at this problem, which is another particular case of the EMX problem. My variables are the expectations of hitting each of those subsets in H. So if H is the class of all subsets, then we have an unlabeled sample, unknown distribution. Uniform convergence fails. If X is infinite, I cannot estimate the probability weight of every subset because I have infinite VC dimension to my family of subsets. But the expectation maximization problem is very easy to solve. If I want to find a set with maximum expectation, I know what the answer is. It's the full set X, because I had all the subset of X. So this shows you that when we talk about expectation maximization, there are cases in which it is easier than uniform convergence. So for uniform convergence, we have the VC dimension that characterizes it. The question we want to answer is, do we have a characterization of which families of random variables are learnable in the maximization notion, which is very applicable. So this is the goal of this paper with Hobbs and Moran and Spilka and Yudayev. We want to characterize which classes of random variables are learnable in this expectation maximization sense. We know that it will be a wider class than those with finite VC dimension. So is there a dimension here? Can we have a purely combinatorial dimension that will characterize learnability in this framework? And again, we are going to use compression. So I'm just reminding you that Littlestone and Varmouth introduced sample compression schemes for binary classification. They showed that it implies learnability. Moran and Yehudayev showed 30 years later than the inverse implication. So we know that for binary classification, we have a notion of compression schemes that is equivalent to PAC learnability. Now, what will happen when we go from binary classification to this more general random variable maximization? So we came up with a new compression scheme that, for lack of time, I will not get into the details of, but it's kind of a similar notion of compression scheme. Rather than going through the definition that is here in kind of light green, I will give an example in a minute. So we have a notion of a compression scheme for this case of Emacs learnability, and we could show that the existence of such compression scheme is equivalent to Emacs learnability. So we could replicate the theorem of that we had for binary classification. We could replicate it for the Emacs problem with a different notion of compression.
Hi, Shai. Can I just ask a quick question about the definition of Emacs learnability? Just as in the case of PAC learnability, I imagine you have some epsilon delta here.
Right.
But then in the PAC, you have a soup over all distributions, right?
Right.
And so same thing here, soup over all.
Same thing here.
Okay.
Right. That's the distribution-free part of my talk. Okay. We make no assumption about distribution. What a guarantee that will hold for all distributions, right?
Okay.
So it's very much like the PAC.
Thanks.
Yeah. So rather than going into the definition of the monotone compression scheme that applies here, I will consider it in a specific subcase. So the subcase is similar to what we talked about before. We look at we have a domain X, and H is the collection of all finite subsets of X. And now the monotone compression boils down to the following game. It's a game between Alice and Bob again. So Alice gets a finite set S, and she has to pick a small subset S prime of S, which is like in the previous notions of compression. And she sends it to Bob. And what Bob needs to do is just to find a subset of X, which is also finite, but it is a superset of S. So the game is as follows. I mean, Alice gets a sample. She needs to send to Bob a few points of this sample, and he should be able to reconstruct a superset of what she had to start with. All those sets should be finite because we are playing this game with finite sets. In more generally, you have a family of sets H. Alice gets a sample of collection of points that belong to one of them. She sends Bob a small subsample, and he should reconstruct not the set that Alice had, but a superset, a supersample. So let's see how we can play the game when you have a domain X and the collection is all finite sets. So the first case is X is finite. If X is finite, this game is very simple. Bob can always just output X. Bob is allowed here to give you any set in the collection, and the collection includes all finite sets. So the set of all of X will always be a superset of what Alice had. What happens if X is countable? So think about this situation as follows. We have a countable set, say the natural numbers. Alice got a finite set of natural numbers. She has to pass the Bob a small subset, and he should be able to reconstruct a superset. This can easily be done in the natural numbers, because what Alice will do, it will send to Bob the maximum point in her sample, and Bob will just give the initial segment up to this point. So Bob can get a superset of what Ali said by seeing only one point. So we know that it's solvable in the case of finite x, countable x. What happens with x is uncountable? That becomes more interesting. So we have here a theorem, which is a completely infinite combinatorics theorem. It says that for every k, the set of all finite subsets of x has compression of size at most k, if and only if the size of x is at most aleph k. So the compression here is a way of this game, is a way of characterizing the infinite alephs, which is kind of a fun observation. So let me just remind you, alephs are the infinite cardinals. Aleph 0 is the cardinality of the countable sets of the natural numbers. Aleph n plus 1 is the first cardinality, which is larger than Aleph n. Cantor's theorem tells that the cardinality of the set of reals is larger than Aleph 0. And Paul Cohen proved in 60 that by the axioms of set theory, we cannot determine which larger cardinal the reals are. So the alephs are the cardinals by increasing order one by one. We know that the reals are above Aleph 0, but we don't know which aleph they are. Why does it matter to us? Okay, so here is the proof of the compression. I will not go into it. We can prove that this collection of all finite subset of x has a compression to size k, if and only if x is of size at most aleph k. Okay, so this I don't think I'll have a time to go to the proof, and also without the board, I don't trust that it can be conveyed. So let's move on. So what did we get? We know that Emacs learnability is equivalent to having a monotone compression scheme. So for Emacs learnability, we can prove the following equivalence. Park learnability is equivalent to weak learnability, is equivalent to a monotone compression scheme of finite size of the type that we've just seen. So if we compare it to what we had with the binary case, only the blue ones remained in the equivalence, the other one are not equivalent. And we also have a quantitative version that tells you that if you have a compression of a certain size, it tells you what is the number of samples that you need for learnability. But so learnability and compression in this notion of monotone compression are equivalent, learnability in the Emacs sense. But what do we get in terms of the finite subset of x? We know that they are compressed if and only if x is of size at most aleph k. So we know, we can conclude that the class of finite subsets of the real line or the unit interval is Emacs learnable if and only if the cardinality of the reals is at most aleph omega. Aleph omega is the limit of the aleph n's. Aleph 0, aleph 1, aleph 2, the limit is aleph omega. It is independent of set theory whether the reals are below or above aleph omega. And therefore, we conclude that it's independent of set theory whether the collection of finite subsets of the real line is Emacs learnable or not. So we get a funny result that learnability of the class of finite subsets of the real line is independent of set theory. You cannot show it's learnable, you cannot show it's not learnable, because it's equivalent to the question about the cardinality of the reals. Okay, so this could be viewed as a kind of curiosity. Who cares about learning finite subsets of the real line? I mean, what we are trying to learn here is find a finite subset that has maximum weight under the probability distribution. So if the probability distribution is uniform over the interval, it's easy. Each of them has probability 0. But if it's, say, a discrete probability distribution, you want to find a set which is, say, captures 2/3 of the distribution, the ability to do that is independent of set theory. But let me push it further. So we can use this result to discuss the question of, do we have a combinatorial dimension that characterizes Emacs learnability? Because we have the VC dimension that characterizes binary learnability. We have all kinds of dimensions that characterize different notions of learnability. What about this Emacs learnability? So of course, in order to ask if there is dimension, I'm going to show you that there is no dimension. We have to be more concrete, more exact about what do we mean by dimension. So by dimension here, we mean a formula which is first order language and quantifies over elements of the class H and quantifies over domain point X. Like think of the VC dimension. It says that the VC dimension is D if there exists X1 up to XD, and there exists H1 up to H2 to the D that shatters X1 to XD. So any such formula that has quantification over points and quantifications over models, we'll call it a dimension. And we ask, can such a formula characterize learnability of Emacs? So VC dimension is greater than D, such a finite character, fat shattering, graph dimension, Natarjan dimension, all the known dimensions fall into this family of expressible in first order logic over H and X. So now it turns out that we can construct two models of set theory such that the reals will be the same, the finite subsets of the reals will be the same in both of them, but the continuum in one of them will be less than aleph omega and the other above aleph omega. So any finite dimension, any finite character dimension, any dimension will be the same in the two models. But in one of them, the class is learnable, and in the other, it's not learnable. So the corollary is that there can be no finite character notion of dimension that characterizes Emacs learnability. So that's a very kind of, this is a more, I think, significant result than the independence of learning finite subsets of the real line. And this says that you cannot hope for a dimension that will characterize this general notion of learnability. That was a question that was already raised by Vapnik, and we are still unclear about dimension that characterizes multi-class learning. And here is indication that could be a situation where we have pack-style learnability and no dimension exists because of this independence of set theory. Okay, so let me just do some discussion of this. Where does this independence of set theory come from? I mean, we are talking about weak learnability. We want to find sample that suffices to approximate a good answer to within a third. Where does independence come in? It turns out that it comes from the fact that when originally statistical learning was defined, it was defined in terms of functions, not in terms of algorithms. The characterization tells you when is there a function that will take samples and come up with a model, but not when there is an algorithm. Of course, we only care about algorithms, but the nice characterization by VC dimension is in terms of functions and not algorithms. So what happens if we go to algorithms? If we go to algorithms, there will be no, if learners are required to be algorithms, there will be no independence because these are finite objects. But what happens is that the characterization that we know of the VC dimension, many of the nice results that we know for learning, for pack learnability, they break down the minute you require the learners to be algorithms and not just functions. So this is recent work with Ruth Urner and my students Sushant Agarwal and Nivasini and Tosca, and we showed that the characterization of binary label prediction with finiteness of easy dimension breaks down once we require learners to be algorithms. We know that ERM will always learn if you have finite easy dimension, but there could be cases in which there is no computable ERM, and everything which is computable will not be a good learner. So that's kind of the next direction to investigate. And yeah, that's the end of my talk. Thank you very much.
Great. Thank you very much for the very thought-provoking talk. Any questions? So maybe I will start out with one question. Can you elaborate on the distinction there you made between functions and algorithms? Is it that functions don't necessarily have a finite description length, and then
right? Because when you look at the base fundamental theorem of binary classification, it tells you that if you have finite VC dimension, then any ERM, I mean, you get a sample and you have a class H, and you want to find an element of H that minimizes the empirical loss. So we know that such an element exists, but it could be that you cannot compute this element. It could be that finding an ERM classifier in a class H is equivalent to the holding problem.
I see. Yeah. Mm-hmm. Makes sense. Any other questions?
So Shai, can you make it, bring it to some practical grounds? I mean, I always thought that these transfinite cardinalities are not important for anything practical.
Right.
So it's actually the first thing you actually show me ever that related to something like a practical problem of learning something real. So show me a problem where this, which I thought until now that can be learned, it actually cannot be learned.
No, yeah, I don't think that this is the, yeah, I agree with you. This is a completely theoretical thing. The thing which is kind of getting a little bit close to practical is that there was a hope that you will have a dimension that characterizes learnability. And as a result of this independence, we can prove that there can be no dimension that characterizes learnability in this general sense.
All right.
Any other questions?
Shai, just I guess a bit more of a philosophical question here. Just learnability defined as a superoverall probability distributions. Distribution free in some sense. Is that really what we want? Is that really what we want, or we just want to be able to, given the data generating distribution, we want to learn with respect to that, not necessarily that we have an algorithm that is distribution free, no?
So it's not completely clear to me what you mean, but what I'm saying here is what I emphasize, that if we make no assumption about distributions, you can say some distributions are unrealistic and we don't have to count them in. But in order to get this funny result, all we need are distributions over finite subsets of the reals. So we can get the same results from just considering all discrete distributions over points of the real line. It's just that as long as you don't know which distribution generated the data, you cannot give a finite sample success guarantee. Is it in the direction of your question?
To some extent, it is. But so essentially, yeah, the question is, what if I restrict the class of distributions?
Right, so that was, I mean, the first part of the talk I was trying to say, if you restrict, say, mixture of Gaussians, you can learn you can know which Gaussian it was, which mixture it was. So this is the other direction. What if under some restrictions, you can really approximate a distribution, then you know everything. And this part was when you don't assume anything about the distribution, what questions can you answer?
Thanks.
Any other questions? Okay, so maybe I'll ask another question. Do you think there might be some middle ground between, I guess, the distribution of free setting and the distribution, no distribution family setting? So is there, could there possibly, some necessary condition that you can characterize learnability on the, and necessary condition being on the assumptions that you know about the distributions?
Right. So I think this does go back to this big question that our analysis, not just in machine learning, in complexity theory also, is basically what we know to do best is worst case analysis. And in reality, worst case never happens. And the question is, which assumptions will still allow us to get good algorithms, good learning or efficient algorithms, and still capture any practical situation that we may run into. And I think that there are several candidates, both in machine learning and in more general computational complexity, for how to restrict rather than doing worst case, looking at more restricted domain and say, this is all we need in practice, and in this restricted domain, we can get better answers. And there are also partial answers in this direction in machine learning.
Mm-hmm. Any other questions? Okay, so if there are no more questions, let's thank Shai again for the very thought-provoking talk.
Thank you.
All right. Yeah, so that concludes today's seminar. And so we'll have another set of seminars next week on Tuesdays and Thursdays. All right. Thank you very much.